In this video, let's look at another type of distribution for discrete data called a geometric distribution. And here are some of the criteria for a geometric distribution. First of all, it has to have two outcomes for each trial, a success or a failure. The trials have to be independent of each other and they have to be identical. So far up to here, this looks an awful lot like a binomial distribution that we discussed in the previous video. The key difference between a binomial distribution and a geometric distribution is that we're going to define the random variable x as being the waiting period before you get your first successful trial or your first successful attempt. So there was no waiting period involved in binomial before. It could happen at any point. So let's look at an example of someone who is a basketball free throw shooter. And let's make the assumption that their rate of success, which we will call P, is 75% or 0.75. And their failure rate, therefore, would be 1 minus P, which would be 25% or 0.25. So what is the probability if they sink it on the second try or their second shot? Well, that would mean that they would have to have had a failure in the first shot, which means they would have had 0.25. And then in the second shot, there would be success. So we can show this as a no and a yes. Okay? And we could figure that out. I just want to show you how to set this up first of all. What would happen, or what would the probability be, if this free throw shooter misses the first shot, misses the second shot, and finally makes it on the third shot? And I'll put a word shot here instead of try, just so that we can put it in the context of the basketball player. So that would again mean first trial is a fail, second trial is a fail, and the third trial is a success. You can see. So this particular shooter had to wait 2 trials before getting their first success on the third one. And you can see a similar pattern. What's the probability for the Xth shot? Well, the Xth shot would have as many failures as it took, and then finally have a bout of success on the next one. Because again, X is defined as the waiting period or the number of failures. Okay? And this is therefore how the equation for geometric distributions works when we're finding the probability. So the probability for a particular value of x when our random variable is defined as the waiting period is just simply equal to the number of failures to the power of x times that one chance then of getting that success the next time around. So let's look at an example. Let's go back to the game of Monopoly. And let's look at the probability of being able to get out of jail. And for those of you who've played Monopoly, you know that to get out of jail, you need to roll doubles. Okay, so how many rolls will it take to get out of jail? So in the case of Monopoly, where you're going to throw a die, you know that when we do our distribution of first die, second die, and summations, that the doubles are all found along the diagonal here, if we have 1 to 6 and 1 to 6 here. Okay? There are a total, therefore, of 6 out of 36 opportunities to be successful in getting doubles, or we could reduce that down to 1 to 6. So therefore, our variable P, or our probability of success, is 1 out of 6, and Q has to be 1 minus P, which is 1 minus a 6, or 5/6. Let's do a distribution table to show a whole bunch of the different scenarios. So in our first column, let's do the number of unsuccessful rolls. Okay, or in other words, this is our little value of x, our waiting period. Let's look at the probability. And then let's also do an x times p at x column here as well, because as you might expect, we're going to go and look at how we can calculate the expectation too. So let's say that there are no unsuccessful rolls. That means that you actually get your doubles on the first time through. So we have 5/6 to the power of 0 because you didn't have to wait. You got that successful outcome on the first try. And so anything to the power 0 is equal to 1. 1 times the 6 means the probability would be 1/6 of that happening. What if you had one unsuccessful roll? Well, then you would have 5/6 to the first times your successful attempt. You would get it on the second try, if you will. This would come out to be 5/6 times 1/6 would be 5 out of 36. And I'm going to go ahead and fill in this column as we go along here as well. X times p at x. So 0 times a 6 would just simply be 0, and 1 times 5 out of 36 would be 5 out of 36. Let's do this a few more times until we get down to, let's say, 5 unsuccessful rolls. And you start to see a really great pattern develop. So if you have 2 unsuccessful rolls, you had to wait 2 turns before you got your successful roll, our equation would look like this. This comes out to 25 times 1 and 36 times 6, which would be 25 out of 216. And doubling this would be 50 out of 216. Jumping down and reducing it, you get 25 out of 108. If you multiply the top by 2, but then divide top and bottom by 2, you'll get in lowest terms here. And we can continue on. We have 3 unsuccessful rolls before our success. We have 4 unsuccessful rolls before our first success, and then we have 5 unsuccessful rolls before rolling the doubles. And you can see that these fractions get kind of massive pretty quickly because of all the multiplications in the numerators and the denominators. And I'll just show you what those start to look like. So 5 to the power of 4 is 25 times 25, which is 625, and 6 to the power of 5, 6 to the 4th, and another power of 6 becomes 7776. And again, this one starts to get pretty fun as well. So you can see that they jump pretty quickly. Now, we could reduce them because we have to take this, multiply by 3, take this, multiply by 4, and so on. I'm just going to say reduce here for now because there's got to be a better way to get to the expected value. We know that E at x is equal to the sum of all those values, but they're going to be in some pretty funky forms. So is there another way to find the expected value? And thankfully there is. It's actually pretty straightforward. The expected value for a geometric distribution is just equal to the probability of success failure divided by the probability of success. So for our Monopoly example here, our probability of success is 1 over 6 on the bottom, and our probability of failure, which goes on the top, is 5 out of 6. So 5 out of 6 divided by 1/6 can be thought of as 5/6 times 6 over 1, which means the expected value, or in other words, the number of waiting periods you would have to get on average, if you did many, many, many trials of this, would be 5 unsuccessful attempts, which means that you would get out on the 6th roll, on average. So you may recall that in the game Monopoly, you try 3 times and then you pay $50 to get out if you can't get out. And you can see that your chances of paying that $50 are a lot higher overall than trying to roll those doubles in a combination of 3 rolls. Okay, let's do another example. Let's look at a paper bag. It has some licorice in it. Okay, and inside the bag, we're going to have 4 red licorice nibs, and we're going to have 6 black ones. Every time you draw a nib out, though, you replace it, which is kind of unfair because you most certainly want to consume it and not put it back in. So what is the probability that the first red nib is drawn after your 3rd attempt? Okay, so let's first of all list out our variables. Okay, our probability of success of getting a red nib There's 4 of them and 10 altogether. So our probability of success is 4 out of 10. You could reduce that down if you want to 2 out of 5. I'm going to leave it here for now. That means our probability of failure would be the remaining 6/10, or getting the black nibs, right? And what's the probability that the first red nib is drawn after your 3rd attempt? So our x value is going to be 3. So after our first attempt, that means we have to have 3 unsuccessful attempts first before getting it on the 4th one. So our probability when we have 3 waiting periods is equal to 3 failures. 6/10, 6/10, 6/10, and then finally success on the 4th attempt. And you can use your calculator to do this, 0.6 cubed times 0.4. You can then multiply it by 100 to get a percentage, and you get approximately 8.6%. So not a great chance of getting a red one after you replace it on your 4th attempt. How many terms would you expect to wait until you get a red nib? Okay. So let's do the expected value here. E at x, when x is 3, is going to be equal to, sorry, just E at x, my bad, I'm still on the previous question, here we go, is equal to probability of failure over probability of success. I'll actually put it over here just for spacing. So we have 6/10 divided by 4/10, which comes to 6 out of 4, which means after 1.5 attempts, or after 1.5 turns, you would expect to draw a red nib on average if you did this over and over and over and over again with many, many trials. Let's look at one more example. A student is on time to leave for his or her job 20% of the time. What's the probability that they will be on time at least once in 5 days? All right, so again, let's begin by putting out our variables. Probability of success, 20%, so we can put that as 0.2, and therefore probability of failure is 1 minus that, or 0.8. Now it says, what's the probability that he or she will be on time at least once in 5 days? At least once. So that means we have a scenario where x can be, she's on time on the first day, she or he. She or he is on time on the 2nd day, 3rd day, 4th day, 5th day. In other words, they don't wait, they're on time the first day. This would be that they're on time the 2nd day, 3rd day, 4th day, or 5th day. So at least once. We have to look at all of those scenarios. So the probability when x is in between or equal to 0 and 4, we've got to do them all those scenarios. So we have success of failure. There's none. He or she makes it on the first day. And maybe I'll just add that in here. First day on time. Okay, and I'm just going to actually work kind of around in a couple different ways because of space here. Then there's one day where they're late and then they make it on time. So this is the 2nd day. Student makes it on time. And then we can go into the 3rd day, which means there were 2 late days, made it on the 3rd day. And then we have 3 unsuccessful days, or 3 lates in a row. Late Monday, Tuesday, Wednesday, makes it on time on Thursday, if we assume a typical work week here to help with the explanation. And then finally, we have late Monday, Tuesday, Wednesday, Thursday, 4 days, makes it on the 5th day. Okay, and again, you could think of it as Monday, Tuesday, Wednesday, Thursday, Friday if you like to. Okay, and so we got to do all of those scenarios added together. Allow your calculator to do that for you, and you should get, I'm going to leave it as a decimal this time, around 0.67. I have 232 here. So if you did it as a percent, it would be approximately 67% of the time. So there's a 67% chance that they will make it on time at least once in 5 days. Okay. Now, this is a lot of work, and this is doing it directly. You could also solve it indirectly. You could do this. You could have 100% probability and then take away the probability of missing all the days, or late all 5. So if they're late all 5 days, you would have 5 unsuccessful trials and no successful trials. So anything raised to the power of 0 is 1. So 1 minus 0.8 to the power of 5 would also give you the same answer. So I just want to show you can do direct or indirect. And then how many days would you expect to wait before he or she is on time? So what is the expected value is what they're asking for. So again, the expected value for geometric is probability of failure over probability of success. We have 0.8 divided by 0.2, which is equal to 4. So you would expect, on average, to wait 4 days before he or she was on time, with this 20% making it on time average for this particular student. And there you go, geometric distributions, similar to binomial, but emphasis on the wait period, and it creates a geometric series as a result. Okay, enjoy your practice. If you have any questions, please let me know.